Okay, welcome to the lecture 5 of the ongoing course Perception Algorithms for Autonomous System. In my last lecture, I covered the basics of Kalman filter. We started your statistical interpretation of the Kalman filter state distribution, a prior distribution, posterior distribution, what is called Markovian dynamics, and how when the measurement is coming, how the predicted distribution is going to behave. So, we talked in details of the Kalman filter. We started some pictorial view of a Kalman filter, actually how you are doing prediction based from your estimated distribution at t equal to k minus 1 using your Markovian dynamics. You go to your predicted state to at t equal to k. Then when the Gaussian measurement is coming, then from the prediction you go directly to the estimated state and estimated error covariance. So, this predicted corrector cycle we discussed. Also we discussed what is the role of Q and what is the role of R in the Kalman filter modeling. In today's lecture, what we will do? We will discuss some more about some basic property of a Kalman filter, which is very important when you simulate Kalman filter for any real time problem, or suppose you do not have a truth, you only have some measurement from some sensor or some hardware. Then how will you know your estimation is all right? So, this is we are going to talk in terms of something called innovation, how to check it we will talk, and then we will take an example, typical vehicle collision avoidance system example, where we will discuss about first how the tracking is done. Okay. First without Kalman filter and then with Kalman filter. So, with this introduction, let me start today's class. So, fundamental properties of innovation. So, you know, suppose now how you test your Kalman filter. Last lecture what I told that you first plot if your truth is known. Suppose your truth is known, you are doing in a simulation environment. In simulation environment, you know your truth. Okay, you simulate your measurement, and that measurement you feed to a Kalman filter. Kalman filter will give you some estimation and estimation error variance. Now, suppose your estimation error is within the plus minus 3 sigma bound of your variance or your standard deviation. That means your Kalman filter is converging. So, this is your say root p. This is say your minus of root p. Okay, and this is your estimation error. Estimation error I am denoting at x tilde. So, if this is converging, then your estimated Kalman filter is converging. So, this means that you are in a simulated environment, you know the truth, but actually practical case you will not be knowing the truth. Truth is a hypothesis, you will not be knowing. You have some assessment of the truth in terms of from a sensor. The sensor is giving you some evidence of the truth. So, how to do that now? Now, suppose you do not have truth and you got some suppose estimate, you cannot calculate your estimation error and all these things. So, you have some estimate. Now, how will you know that your estimation is right? There is a way to do it. So, something very important property in Kalman filter is called Kalman filter innovation. What is called Kalman filter innovation? In some book it is referred as Kalman filter residual also. What is residual or innovation? It means the difference between your measured state and the measured value, measurement minus the predicted measurement. So, the discrepancy, because if you remember now when I was telling you this least square and all this thing. So, they are also when our cost function is the measured minus predicted. So, measurement, actual measurement minus predicted measurements. Same thing is called innovation. So, your zk is your measurement minus h into hxk at given k minus 1. So, the predicted state. So, predicted measurement. So, the difference is called your innovation. Now, innovation has many important properties that we should know. First thing is the unbiased estimation. Kalman filter is called sometimes blue estimator. Blue means best linear unbiased estimator. Linear all you know because your state and measurement equations are linear, nothing like that. Unbiased means yesterday I told or last class I told that your expectation of your errors, estimation errors. So, expectation of your prediction error is equal to 0. All errors I am noted using this thing x tilde, and estimation error is equal to 0, right. Once this is 0, obviously you can say if your Kalman filter is unbiased, then your innovation is also average of the innovation is 0. When I say E term, E means expectation. Expectation means simple averaging, simple ensemble averaging. It is called ensemble averaging. And for a ergodic process, if you remember your probabilistic theory or any probabilistic course, your time average equal to your ensemble average. Okay. So, it is just an averaging. So, averaging average value of this ensemble average of your residual is 0 if your estimation is unbiased. And second very important thing is your innovation error covariance. You can calculate it algebraically, it is very easy to calculate it. And this is actually innovation error covariance actually is used for your Kalman gain computation for your correction cycle update. Okay. Now, there is a very important thing. So, if suppose there is a bias has come in your estimate, you can clearly plot your innovation. Even I also told this yesterday, you can clearly plot your innovation and you see instead of having it 0, it is kind of a biased. It could be fixed bias, it could be variable bias, whatever, but it is kind of a biased. So, that means you can tell that your measurement origin has an uncertainty, that your measurement is having some external bias is coming, you either need to correct this bias or you otherwise your estimation will be biased, your Kalman filter assumption is violated. Okay. Suppose you are operating in a navigation environment and you are given some gyro data and you want to fit it some state you want to estimate, your gyro is having the bias. Okay. So, that bias if you do not correct it using a secondary sensor or secondary this thing, you get a biased estimate of your state. The same thing here is also. So, that is very important that you need to check out that your measurement is bias free, number 1. So, this will give you one correction. Now, second thing is that this is Gaussian. What is Gaussian? This innovation error will be Gaussian. So, when it is a Gaussian, then it is a very well known property of a Gaussian distribution is that normalized residual error square, very big term, but very simple. It is the norm of innovation, the norm of innovation. What is the norm of innovation? You just see that norm of innovation is this. Okay. So, with this you can see this is actually the transpose into covariance matrix inverse into this thing. Okay. So, if it is a scalar thing, you can obviously say that z tilde k square divided by your sigma square, if it is a scalar, say innovation is a scalar. Next example, I will take a scalar example only, not a matrix and all. So, this fellow is chi-square distributed. This is very, very important property. In the when we will start the tracking, the whole tracking measurement validation in the first line is based on this fundamental principle. So, this is very important, we should know it. So, the norm of innovation is chi-square distributed. Okay. Once it is chi-square distributed, if we take a moving window sum, then we can tell that it is having some degrees of freedom. Okay. And you can check from your chi-square table that what is the percentage probability concentration for your innovation normalized sum of innovation. So, if your this thing, so acceptance interval is determined. Suppose if the probability of your windowing sum of the innovation is belongs to R1 R2 given hypothesis 0 is 1 minus alpha. So, if you take alpha is equal to 0.05. So, 95% confidence interval with two sided interval like this, your probability 95% will be probability concentration of alpha. So, if now you do not know how to validate your estimate, you check this, you always check this, you do a moving window sum of your innovation and see and run a simple chi-square test. If it is a chi-square, well and good, and if it is unbiased, the mean will be 0. Okay. So, this will give you an indirect way to tell guys my estimate is proper when you do not have a truth. If you have a truth, then you can plot the error and all, but actually you will not have a truth. Okay. So, this is an important property of innovation. With this now, I would like to demonstrate or kind of explain the Kalman filter in a practical example. This is a very, very simplified example, oversimplified I will say, but it is good to have a Kalman filter example, because I feel this is the best example that can demonstrate the need of tracking plus a Kalman filter. We consider an vehicle collision avoidance system. It's simple car, nothing UAV or so. Okay. So, just take a one dimensional tracking problem of a vehicle collision avoidance system. Suppose your vehicle is mounted a sensor. A sensor is mounted on your vehicle, say a simple radar or simple say camera, whatever you feel, whatever is good for you. You mounted it, it is giving you relative distance from your vehicle to your front vehicle. So, I am naming the vehicle where the sensor is mounted is your ego vehicle. Let us use this terminology. It is ego vehicle, and the ego vehicle, the sensor where it is mounted, it is looking at the preceding vehicle, say. There is another say preceding vehicle is there. So, this is your vehicle, this is a preceding vehicle. So, when you are doing this thing, you want to design a collision avoidance system, you will have two states. One is the relative distance from your vehicle to the preceding vehicle, number 1, and number 2 is what is the rate of change of it. So, that is called velocity. So, relative distance is simply called range and the range rate. Okay. So, when you say, so your states will become as a simple, you can write in a continuous form is like this. So, d dt of rho dot, rho is your range and rho dot is your Doppler or velocity, range rate, you can say. It is simple phase variable formulation, you can write it like this. What is the Wt? Wt is some unmodeled acceleration. So, suppose say, so because rho double dot I have modeled this constant, but actually I do not know that there should be some unmodeled dynamics can come. So, that is why some noise, random excitation noise I have put just to model my ignorance about the physical process. So, this is actually your Q, the covariance is actually your Q. Okay. And the sensor, whether radar, camera, lidar, whatever you have installed here, say it gives only the relative range measurement by some means. Camera won't give, but it is possible to give if there is LNR and all these things are there. So, they say this you have the position measurement or the relative distance measurement. I won't use the position because if you want to have the, if you want to do position, then you need to have the coordinate system and you need to know with what respect of your coordinate system your ego vehicle position is. So, that is why it is best thing to do is using the relative distance or range. So, it is like this, okay, that is contaminated with wide Gaussian noise. Now, you do the discretization. I will show the discretization in the next lecture. So, but just imagine it is simply you just do e to the power at is equal to your phi of k, it will be I plus at, okay. T is your sampling time, I is your identity matrix, A is this matrix, T is your sampling time. So, if you do it, you get 1 T 0 1, simple. And if you simple, this is say W T is here. So, your B matrix actually becomes 0 1, okay. So, there is a formula also that I will tell next. So, if you do this, you discrete equivalent, you get T square by 2 by T. Okay, I will show it in next lecture. So, I won't discuss it here, and this is a discrete sequence of your range measurement. With this, first thing what we will be talking is something called very interesting, something called very old tracking technology. This tracking technology was used in Second World War time. Second World War time, there was not so much computer, there is no such much computational capability, and even Kalman filter was not invented those days. Kalman filter was invented in 1960s when Kalman, the Hungarian mathematician, invented this technique. So, that time how the British radars or German radars used to track your target, your ship or your aircraft and all using your ground radar. British first used the ground radar against this German attacks and all. So, how they use, what they use it? So, there is something called alpha beta tracker. Alpha beta tracker is a constant gain tracker. There is a particular intention why I am telling this, because if I draw the alpha beta tracker and then I go to the Kalman filter, it will be useful for you. So, you remember your Kalman filter estimated state equation. So, estimated state, it is estimated state, this is your predicted state plus this is your correction. Correction means Kalman gain into your innovation. Alpha beta tracker, there was nothing called Kalman gain. it is only some constant gains. Okay. One gain for your position estimate, one gain is your for velocity estimate. So, in our problem now, I have my relative distance and relative distance derivative, that is my range rate. These two I have. So, I can write my equations like this, f is equal to your 1t01 and this is my predicted state equation, right. And when I do your matrix simplification and all, you get this is for your range and this is for your velocity. So, velocity actually I am not doing any time update. Range, it is simply some integration. This is a simple Euler integration I have done. So, your range thing is equal to the previous range plus some time into velocity range rate. Okay. Simple thing. So, now I calculate the predicted measurement h into this thing, okay, and this is my say Kalman gain when I am or my alpha beta gain. One is position will be incorporated with this alpha gain and velocity will be factored with this gain, velocity error. Alpha is within 0 to 1, beta is within 0 to 2. How to select the alpha beta value we will discuss. So, with this you get two equations, one is for your position, another one is for your velocity. So, your position equation, this is your predicted, right, plus alpha into innovation. Okay. Similarly, beta, this is your predicted, this is your beta by t into innovation, measured minus predicted measurement. Okay. So, you can now you can just clearly you can signify there is only state update, there is no covariance update, there is no online gain update because alpha beta is constant, okay, in alpha beta filter those days, because that time there was no computer, there was no Kalman filter, but this thing works actually. Actually, if you do if a target is moving in a nearly straight line, this thing works. If it is moving with a acceleration, then there is something called alpha beta gamma tracker that works actually. Okay. So, with this now how to choose this value? So, there are two ways, either I want fast tracking or I want measurement, I want my tracking noise to be minimum. So, suppose this is actually say your truth, so this is your truth, and suppose I have chosen a very small alpha will delay the convergence. So, it will start tracking from say this time, and this time say it is this error is continuously building up, then it is coming down, but the noise level is small. And another thing is called, if I want to do now fast tracking, then I have to give little bit higher value close to 1 and all this thing I want to give. In that case my this thing will be bigger, but I will get jig 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 jig. So, these are all practical problems in a alpha beta filters, okay. And that is why the more sophisticated version has come, where my these gains are online calculated, plus I will be updated my variance in each and every dt, okay. So, you understood. So, this is a problem intentionally I solved using alpha beta filter. Now, the same problem I will be solving using Kalman filter and how it looks like. Now, Kalman filter what I told, now I will not have any alpha or beta gain, my gains will be computed each and every dt as per my Kalman filter cycle, okay. My covariance will also come into picture. Previously what happened, my only states were coming into picture, but now my covariance will be coming into picture. So, state is anyway, state equation is same, remains same, only you change your alpha beta using k. Your predicted covariance, your output covariance, innovation error covariance, you got it, and this is your actually Kalman gain. Actually, I have solved the matrix by my hand and this is your actually Kalman gain, okay. You can yourself do it, just take a one example and do a simple matrix multiplication, it is possible to do it by hand. With this you get your estimated state is this. So, this is actually now your alpha, this is actually say your beta, but they are online each and every dt they are changing, and this is your rest of things are same. And estimated state covariance you can see it like this. So, I minus Kc, okay. So, now your gains are changing, gains are function of your error covariance, and error covariance is also changing each and every dt. So, this is the simple Kalman filter implementation. With this now I need to now see, this is a representative plot, again I have not write the Kalman filter, but you can do it yourself very easy, just a 2D example you can yourself see. This is a simple representative plot, if you plot the error it will be coming simply like this and I can bet for it. So, what it happens, so here it is actually your instantaneous error. your instantaneous error. So, you can see your instantaneous error, initially the error was large and gradually by and by it is kind of smoothing it out with a very kind of small value, say 0.05 or 0.01 or something like that. Even it will actually, if you do this thing, you will get the mean value is kind of a 0, because your estimation is unbiased. So, it a very less value, very less value. Okay. In simulation, you will get near 0, even you can get it 0.001 also, something very similar. So, and your estimation error. So, this is your estimation error. So, xk minus x at k, which I am notating at x k k, this is my error. So, my error, this is position error, and same will be for velocity error. So, once you do this, you can clearly see that this guy is kind of converging. If it is converging, that means your Kalman filter is working fine. If it is not converging, that means if it is diverging, then your Kalman filter won't work. So, Kalman filter convergence, so this is very important property of a Kalman filter. So, this is your P time, P means actually suppose P11, P11 is actually your covariance of what I should say, your covariance, first covariance of your position error covariance. Okay. So, there are, if you see this P has two things, one is P11, P12, P21, this is our symmetrical matrix. So, I can write P12 itself and P22. So, this is your position error covariance, this is your velocity error covariance, and this is cross covariance, symmetric matrix. Okay. So, P11 is your position error covariance, the root P is your standard deviation. So, it should lie in this bound, root P and minus of root P. If your S error is lying within this bound, that means your Kalman filter is converging. Okay. So, this is all single run. Now, people also do something called Monte Carlo stress statistics. What is Monte Carlo run? Monte Carlo run is called when normally in linear filter, honestly speaking, I do not believe that you need to do a Monte Carlo run to check your filter convergence, but for a non-linear filter, yes, you should do it. Okay. Linear filter, this should be sufficient, but you wanted to do a Monte Carlo, it is good, but non-linear, it is mandatory. What is Monte Carlo run? How you simulate Monte Carlo run? Monte Carlo run is simulated by changing the seed or the state of your pseudo random number generator in whichever programming or the scripting language you are using, MATLAB, Python, C, C++, whatever you are using, I do not know, whichever thing. So, everything, because if you are using MATLAB, if you are using Python, C, everyone has their own pseudo random number generator, and pseudo random number generator always have only one initial start point, that is called the seed value, or state value. Now, the state value you can change each of every run and you collect the error. So, it is like this. So, your x tilde k k, your estimation error, this is say sample 1, sample 2, okay, maybe, and say then the dot say sample 100. Okay. So, with this you calculate the error, take the errors. So, this is say E1, E2 for each and every state, and say E100, say you have taken 100 Monte Carlo run. By changing the seed, you simulated each and every measurement and you have collected the errors for each and every sample. So, matrix you have done for each and every state. Now, you calculate the RMS value across each sample. You know RMS value, how it is calculated? Summation of EI square divided by number of run. Here I have taken number of run is equal to 100. You can take 100, 200, 300, whatever you do. The more run you take, the more smoothing effect will come. And now, you plot your RMS error, or you can take the error variance also. If you wanted to take like this, you wanted to do it with error variance also. Once you take the error variance, basically you are numerically calculating your P values, your P11 and P22 values. Actually, you are numerically calculating using some of this thing. Okay. So, with this, if you calculate and plot your error is going to converge and it will be very smooth. Here you see when you are steady state, there is some small jerks here, up down is there, but here if you see this, it has to be a very smooth value. So, that means your filter is converging. Will it converge to 0? No, it won't converge to 0. It will never converge to 0. There will be some very minimum error will be there, minimum error will be sitting there, and for a nonlinear Kalman filter this is must to do, because there are examples. We can show one example also in some part of a tracking lecture series. If in one case your nonlinear filter may backfire, especially if you are using first order extended Kalman filter, all this kind of approximation, it might backfire, and then Monte Carlo, if one run it diverges, then you can see it won't be converging like this. But for linear filter, 100% case it will converge, it should converge. You do not need Monte Carlo test statistics in a linear filter, it is not required. But for nonlinear filter, obviously yes. Now, what is the minimum mean square error bound of this Kalman filter? Okay. So, that is something called, I will be teaching it in the next subsequent classes, very briefly, is called Cramer-Rao lower bound. Cramer-Rao lower bound is the theoretical minimum mean square error bound or RMS error bound, you can say, which your estimator physically the error should do. Now, your estimation error, the error whichever you have plotted here, if it is kind of going near to your Cramer-Rao lower bound, that means your estimation error is, your filter is kind of converging and it is going to this thing, filter is doing its job. Okay. So, that means actually the filter is kind of converging. Okay. So, you may ask me one question that, okay, I understand my filter is converging. Now, I have used say filter 1, say a Kalman filter, I have used say a Kalman-Bussy filter, anyway a continuous version is called Kalman-Bussy filter, or I have used say some Gauss-Hermite filter or Gaussian sum filter or simple some particle filter. So, you if you are working in a kind of a master's thesis or even PhD thesis for yourself, you would like to compare the performance of this filter by plotting the RMS error of each and every of your filter, and you can see which filter is giving you the least error. Okay. I will show in the nonlinear filters, people used to compare these nonlinear filters on a particular problems, and the comparison will be in a Monte Carlo fashion, and Monte Carlo fashion the RMS error which one is close to its theoretical bound. It will never touch the theoretical bound, believe me, because that is the minimum mean square error bound which Cramer-Rao lower bound signifies you. Okay. There is a possibility also to way also to calculate it. So, which filter is giving you the minimum bound, that will be your optimally best estimator. Okay. So, this is all about just a kind of a thing. So, how you want to test your Kalman filter convergence. Two more thing I will tell, then this lecture will be completed. Now, I will tell you the impact of Q and R. Okay. First, let me start with Q. Q is, I already told, it is a process filter mismatch or truth filter mismatch in my last lecture. So, your model is very kind of replica to your actual thing, then your Q, then it is fine, then your then you should take Q very minimum. Here in this example, in vehicle collision avoidance system, what is my this thing? My model is a simple constant velocity model 1t01, okay, or maybe I can go here, this one. Okay. So, now I have, this is my Q or whatever process noise covariance or my due to my unmodeled dynamics. Here what should I do? I will keep Q my higher value or Q lower value? I must keep Q actually very lower value, because this is actual dynamics. I am modeling one, this is my vehicle and this is my ego vehicle, I will say name as ego, and this is my preceding vehicle for which I wanted to make this thing, okay, make this distance. So, this is my rho and this is my rho dot. This is a very proper dynamics. This is not a kind of a this thing, any unmodeled dynamics and all. So, here even my ego is also kind of moving in a straight line, I have something. So, if I put now higher Q, what will happen? Then I do not trust my constant velocity process, and if actually your measurements are simulated from a CV model, then you can definitely expect this noise is going very large. Filter will be converging, I do not mind, but your noise will be very larger if you simulate the measurement from a accelerating or a kind of turning vehicle, if you do this, right. Now, if you are moving in a constant line, this will be thing. So, this is the choice of Q. You need to be very judicious about your model. Now, suppose you are using a constant acceleration model. So, you have constant acceleration rho dot, rho double dot. So, your model will be 1 t t square by 2 0 1 t 0 0 1. So, range, range rate and Doppler rate, all the three things now have been incorporated, assuming that my it is accelerating and all. So, in this case, but if it is a constant driving car, then you should use a lower Q, then lower Q means you do not have actually you want to give trust to your model, okay. You want to give trust to your model. If I increase the Q, that means I do not have any trust of the model, I will trust on my measurement process, that is all about, okay. So, Q thing is the truth filter mismatch is a very, very important design parameter for any Kalman filter simulation. Okay. So, if you do not model your Q properly, then or anyway it is experimental, you can find it out, not a problem, but Q is the key design parameter. So, Q again I am repeating, Q is your truth filter mismatch or process filter mismatch. If your model replicates to the real world, good. If you are confident, you must choose a lower Q. If you are not sure that this model may be some difficulty with my real world, then you should choose higher Q. Higher Q means it will give more weightage to the measurement, lower Q means it will give more weightage to the model, okay, in your Kalman filter update equation. So, if higher Q means it will trust more on this correction factor, lower Q means it will have faith on this factor, okay. So, this is all about the Kalman filter, this thing, and thank you for your time. After that, we will be covering the subsequent lecture, okay. Thanks.